the concepts of units and dimensions, which is also a chapter of class 11, and we will see how the different units have derived. Okay, so basically there are few fundamental units such as length, mass, time, electric current, thermodynamic, temperature, which is measured in Kelvin, right? Luminous intensity, candela, and amount of substance, that is mole, right? So these are the fundamental units. Okay, so what I said, one is the fundamental unit which we have learned till now, right? And the another is supplementary units. So there are basically two supplementary units as of now, the radian and the steradian, right? The radian and steradian. Okay, these are the supplementary units. Supplementary units. Okay, and the matter of our concern, which we are going to learn today, is the derived units. Okay, so today what we will cover all is from the derived units. What is the derived units? We will see. As you can see that this can be found by combining fundamental units. Okay, the units of any derived unit depends upon one or more fundamental units. Okay, actually, in other words, we can say that dimensions of a physical quantity, so how its unit is related to the fundamental unit. So the relation established of that physical quantity, of any physical quantity, relation is established with fundamental unit, right? So basically this is the fundamental unit which we are understanding now. So there are various fundamental units with us as of now. Okay, these are the length, right? Length is denoted by L, right? And this is kept into this big bracket, right? This is the length, right? Now another unit is for mass. The unit of mass is denoted by M. So the representation is done like this, capital M in the big bracket, right? This is for mass, right? Similarly, for time, it is represented as this T, T kept into a capital bracket, right? And one another unit is charge, Q. So we also know I is there, that is current, but it is generally represented by Q by T. Current is charge flowing per unit time. So current is also represented into the form of Q. So this is for the charge, this is for time, this is for mass, this is for length, right? And for the temperature, the unit is Kelvin, but we generally write it as T, right? And one another is there, that is luminous intensity by C, candela. So that we will see for any further examples, right? So we'll simply take few of these examples. Suppose there is a displacement, right? So when, what is the displacement? What is the formula of the displacement? The shortest distance between 2 points. Okay, the shortest distance between 2 points. So basically whatever it is a distance, right? So distance will be coming under what? L. So the displacement, the dimension of displacement will be L, and it is represented like this, right? Now we are coming to velocity, right? Velocity. So what is the formula of velocity? Just remember that the formula of velocity is displacement by time, that is displacement by time. So it can be represented as, what is the unit of, what is the dimensions of displacement? It is L, which we have derived over here, right? And this will be divided by the dimension of time. What is that? Dimension of time is T, right? So it can be written as, when T will be coming into the numerator, it can be written as LT minus 1. So this is the dimension of velocity, right? Now you can take some further example as of I will also explain the source of, as I put the source of gravitational potential and electric capacity. Okay, I will explain those examples in later. But before that, I will take the fundamental units. One we have taken displacement, one we have taken velocity. The another example we can take is acceleration. Okay. So what is the acceleration? What is the formula of acceleration? Okay. The formula of acceleration is displacement by time square. That is, just remember the unit. If you forget to calculate the dimension, just remember the unit of that particular physical quantity. So the unit of acceleration is meter per second square, right? And what is the unit of meter? Meter is a part of length. So the dimension of length will be taken into the numerator L, right? Divided by s square, second square. So s will be coming for time, right? So it will be t square, like this, right? Which can be represented as L t minus 2. Just remember, students, in the dimensions we are not keeping anything into the denominator. Okay, it will be kept like this, right? So this will be the dimension of acceleration, right? Now we'll take some further examples. Let us take the example of electric capacity. Okay, so before electric capacity, I want to just take you to the for the dimension of force. Okay, what is force? The dimension of force, just remember, force is can be represented as m into a, right? And the dimension of m is like this, and the dimension of acceleration we have already calculated. You can see lt minus 2. So it will be lt minus 2. So it can be represented as mlt minus 2. So this will be the dimension of force. Dimension of force is mlt minus 2, right? Now we can take another example of work or energy. Okay, so for any work or energy, work is said to be done when force is applied up to certain distance, right? That means force into distance, right? F into s, right? So what is the value of force? Dimension of force is mlt minus 2. So just write it from here, mlt minus 2. Whatever we have already derived, that we are not going to take over here now. Okay, the force dimension of force is mlt minus 2, and this is displacement. So what is the it is a length. So for length it will be L, right? So into L. So this will be coming as m L into L. Same basis, power will be added. So power of 1 here and 1 here, this will be L2 t minus 2. So this is the dimension of work and energy, right? So this is calculated over here, right? Now we can also take some example of, let's say, frequency. What is the dimension of frequency? Frequency, what is the dimension of frequency? Frequency is 1 by time, right? 1 by time. So when t, what is the unit of, what is the dimension of t? It will be t. So when it will be coming into the numerator, it can be represented as t power minus 1. So t power minus 1 in the written into this big bracket, this will be the dimension of frequency, right? I hope this is visible to you. T power minus 1, right? Now after this we will take another example. Let's say pressure. I'm taking some basic physical quantities, and even you can put up if you want something. Pressure, what is the definition of pressure? Pressure is the force applied per unit area, right? Force applied per unit area, right? So what we will take now, we'll take the dimension of this force divided by dimension of this area, right? So dimension of force, we have calculated mlt minus 2. Just use it over here directly rather than finding one again and again. Okay, so this will be ml t minus 2 for force divided by area. So area, for area, just remember any 2D, any two dimensional object having an area, then even it can be an anything, a square, circle, rectangle, or whatever. But you can just remember the units for that particular physical quantity if you are confused at any place. So for any, for area, you remember the unit as meter square, centimeter square, decimeter square, decameter square, or whatever, or kilometer square. So this is length into length square, right? So it can be written as L two times, right? So when all goes into the numerator, it will be coming as M. One L will be cancelled with this, and one L left into the denominator will come into the numerator. So this will be coming as M L minus 1 T minus 2. So this will be the dimension of pressure, but this is not written like this. This is kept in a big bracket. So this is the standard form where the derived unit of pressure can be written over here, right? Now, what we will see? We will see some examples of, let's say, moment of inertia. Moment of inertia. For moment of inertia, just remember the formula m into r square. So m is mass, right? R square is length square, right? So it can be written as the unit of mass is m, right? Unit of length square will be like this, L square, and when you join it, it can be written as ml square. This is the dimension of moment of inertia, right? Now we'll take some more examples from just as a gravitational potential or gravitational potential or capacity. Okay, so before that, I will go through the basics of physical. So we can take the example of let's say heat. So heat is also an energy. Okay, heat is also an energy. So heat is also an energy. So for energy and work, what we have derived? Energy and work. For energy or work, what we have derived? It's force into displacement, right? And for force, it's mlt minus 2, right? For force, we have derived the dimension of force as mlt minus 2 into displacement. It's a length, right? So it will be like this. So it will be coming as ml square t minus 2. So this will be the dimension of heat. This will be the dimension of heat, ml square t minus 2. So we can see this was also same for not only heat, any kind of energy. The dimension of any energy will be ml square t minus 2, right? The dimension of any work is also equal to ml square t minus 2. Okay, so just remember the definition or the unit of that particular physical quantity, then the derived unit of that particular physical quantity can be written and can be derived in the form of the basic fundamental units as length, mass, time, charge, right? Like this. Now, let us see some example of what is the unit of charge. Charge. So this is charge is represented as q, okay, and q is the fundamental quantity. So it's simply written as in the big bracket q. The unit of charge, the dimension of charge is q, okay. What is the dimension of current? What is the dimension of current? Current. So just remember the definition of current. Current is charge flowing per unit time. Charge flowing per unit time, right? And you remember the changing the pen. You remember the dimension of charge is q, like this, right? And what is the dimension of time is t, right? So it can be written as q t minus 1 because nothing is left into the denominator of any dimension. So qt minus 1 is the dimension of current, right? We can take another example apart from current. Mm, let's say maybe current density. So what is density? Current flowing. What is the dimension of current density? So just remember the formula. Current density is current flowing per unit area or area. And what is the unit of area? It's L square, right? L square kept into the denominator, right? And what is unit of current? Is qt minus 1, right? Remember it? So it's qt minus 1. So when you combine all these together, this will give you L minus 2, right? When this coming to the numerator, L minus 2 q t minus 1. So this will be the dimension of current density, right? We'll take some more example. Okay. So I have explained even all the basic fundamental physical quantities. So whatever the sorts which I put into the channel, I will explain those over here in details. Okay. The electric capacity. What is the electric capacity? Let me, yeah. So for electric capacity, just remember the formula. For electric capacity, what is the formula? The formula is electric charge by electric potential. Okay. So electric charge by electric potential. What is the unit of charge? It's Q, isn't it? By potential. By electric potential. Right? So this is the definition. So this is the definition. Now, what we will do, we will simply, the electric charge by electric potential is the definition of electrical capacity, right? And the dimension of charge is Q. This is known to you because this is a fundamental quantity, right? So the no derivation will be there, no derived units will be there for charge. For electric potential, what we can see? For electric potential, just derive it. For electric potential, whatever is there into the denominator, just find it out. For electric potential, what is that? Electric potential is the work done in carrying a charge, right, from one point to another. That means the definition, as per the definition, we can write electric potential can be written as work for that particular charge in carrying that charge from one point to another. This is the definition of electric potential, right? And for work, we can write force into displacement, isn't it? And for charge, it's already q, right? Now, for force, the dimension of force will be mlt minus 2, which we have shown earlier how to derive it. So the force dimension is already derived to us. So just write it over here. Into displacement, the unit of displacement, dimension of displacement will be L, because it's a distance, right? Distance and displacement both are having the same dimensions of L, right? Divided by Q. So this will give you ml square t minus 2, right? ml square t minus 2 and q minus 1, because nothing is left into the denominator. That's why q come into the numerator. Now, as per the definition of electric capacity, C can be written as q by electric potential, q by potential. So in place of q, it will be simply q. The dimension of q will be like this, right? Divided by the dimension of electric potential, which we have derived, ml square t minus 1 q minus 1, this value. Okay, so this will be coming into the denominator, right? So this will be giving you ml square t minus 2 q minus 1. This will give you the value m minus 1 L. Any other L over here? No. Then simply this L will be coming into the numerator. So this will be coming as L minus 2, right? This Q, when going into the numerator, it will be Q square. So Q square, and T when coming into the numerator, it will be T square. So M minus 1 L minus 2 T square and Q square. This is the dimension of electrical capacity. This is the dimension of electric capacity dimension. M minus 1 L minus 2 T square Q square. So whenever you are seeing any dimensions, just go to the definition of that particular physical quantity. You just remember the unit of that. When you are remembering any of that, then you can easily calculate the dimension of that. Okay. Now we'll calculate the dimension of gravitational potential. Okay, which I have also put into the shorts. So for gravitational potential, dimension, let us calculate it, the gravitational potential dimension, right? So the what is the definition of gravitational potential? So as per the definition, gravitational potential can be written as the gravitational potential energy by mass, right? So this is the gravitational potential energy. So just forget about the prefixes. Just mark the word energy over here. This energy, right? So for energy, you know, for energy we have already calculated, right? That is for heat energy, heat or work or whatever. It is the energy, the dimension of energy is ml square t minus 2, because this is force into this force into displacement. This will give you the dimension of energy or work as ml square t minus 2, right? So we will simply, as per the definition, it's a gravitational potential energy. So energy is the word over here, right? Divided by the mass. So this is also a fundamental quantity. Okay. So for mass, we can simply write it as, put up the fraction first. For mass, it will be m into the denominator, right? And for the numerator, it's an gravitational potential energy. So basically this is energy. So energy is force into displacement, s, f into s. I'm just simply writing the definition, so that's why this small bracket is used, right? For force, it is m l t minus 2, and for displacements it's l. So this will be the dimension of energy or work, right? Divided by this mass m, right? This will give you, you can, when this will give you, you can see here m and m in the numerator and in the denominator, it will be cancelled out, right? And l and l will be multiplied, so this will give you l square and t minus 2. So this is the dimension of, gravitational potential. This is the dimension of gravitational potential, right? So students, in this way we can derive the dimension of any physical quantity, whichever is there in front of you, right? So just try to correlate with it, with its dimensions, its definition, its unit, right? So we have derived, since it's meter per second square. For meter it's a length. For second square it's a time. So you need to just come up with or any derivation in form of these fundamental units, right? These are the fundamental units: length, mass, time, charge, right? And already explained what is c, right? What is c? It's a luminous intensity, right? So you can derive any of the dimensions into the form of this, right? So in this way we can wind up today's session. For any query you can put up into the comment box. Yeah, we can also derive for other, but let's see. If you have any specific heat, for a specific heat or any energy or work, we have already seen for work and energy ml square t minus 2. Just go with the definition first, okay? And along with the definition we can derive the derived unit of that particular dimensions of that particular physical quantity, right? So in this way, with this calculation or derivation of the gravitational potential energy dimensions, we can wind up today's session. So thank you so much for watching, students. Take care. Bye bye. Thank you. Yeah, you can put up into the comment box, and for further details you can see through the playlist as shared into my channel. Okay, thank you so much for watching. Bye bye. Take care.